Okay, let me start with a quick review and then we can solve some problems and finish this. So I think this is the last class, and I want to look back and try to form like a main picture of this class. And the general idea was like that. So we had charges in the universe, right? Positive and negative charges, and these charges gave rise to forces among each others. And then we said, okay, there is actually a nicer way to describe this. And we introduced something called electric field. It was related to force, but it was different from the force. And then later we introduced something called electric potential. And then we saw there were like some applications to these, like you could think about like capacitance and electric energy storage and things like that. And then we introduced motion of these charges. When the charges move, they give rise to electric currents. And as you pass this electric current in the circuits, you have resistance. And we, for example, analyzed so-called DC circuits, some circuits with electric field elements and resistor elements. And we've seen some interesting behavior. In the last part of the lecture, we introduced magnetism. At first, magnetism looked like a different beast from the electric field. But even in the beginning, we already noticed some similarities. And then when we talk about sources of magnetic field, we saw motion of charge, the charge you introduce in the beginning of the class. If it moves and if it gives rise to current, that current gives rise to magnetism. Right? And then if there is like a magnetic field, and this magnetic field is changing in one form, or better to say, if the magnetic flux is changing in one way or another with respect to time, we saw that it gives rise to EMF. And EMF is kind of like an electric field, so that actually completed the circle. You started with electric charge and electric field. Charge current gave rise to magnetic field, and change of magnetic field and magnetic flux gave rise to an electric field. This is, I think, one of the triumphs of electromagnetic theory. It unified two seemingly very different forces in nature, electric forces and magnetic forces. I think if you want to learn one thing from this class, learn this and remember this. And like, let me just repeat what we said yesterday. Yesterday, we talked about mutual inductance. Basically, if you have two coils next to each other, then you pass a current from the first coil, the change of flux in the second coil will induce an EMF. And we describe it in this form. And we said, if you calculate this induced EMF, the coefficient in front of the dt, in this experiment, we are thinking of like a current that changes with time. The coefficient in front of this dt is mutual inductance. And in general, mutual inductance of coil 1 with respect to coil 2 is same with the mutual inductance of coil 2 with respect to coil 1. So we said this one. We saw some examples, and actually we said, even if you have a single coil, there's no other coil here, this is just one single element, this inductor has its own inductance, and we call it self-inductance. And the way we calculated it is like, okay, we first said there's like a magnetic field proportional to current, and we said total flux divided by current is going to be self-inductance. Okay. And this if the dt is bigger, that means current is increasing with time, then the induced EMF by Lenz's rule is going to be negative. And if the IDT is negative, again, by by Lenz's rule, induced EMF is going to be positive. That's why we call it like some kind of reactance or impedance sometimes. And this is the circuit element we use for this tool. So some examples, and finally we introduce energy storage in a magnetic field, and we considered an inductor, and we showed that it's actually exactly, very much similar to a capacitor. And the electric field in an inductor was like something like this, 1/2 Li squared, whereas electric field energy, so this is the magnetic field energy in the inductor, this is the electric field energy in the capacitor. There's like almost 1-to-1 correspondence. And we converted this form to an expression purely in terms of B, which was like this. And we saw that this is actually also exactly like electric field case. And we talk about LC circuits. If you have a battery and if you close the switch, the current starts flowing. Initially, the current is 0. This inductor completely blocks the current for early times. But as the time goes on, it's going to reach to a state as if there's no inductor. It's only the resistor. There's also like putting this element in the circuit gives rise to a kind of delay in the current. That's why we call it impedance or reactance. Or if you initially reach this steady state, maximum current, and then change the position of the switch, and then you are going to have something like this. Now there is like an initial current, and even though you disconnected the battery, it takes a while for your circuit to notice this. There's like a delay here. There's like a reactance. All right, then I'll start. So here's the first suggested problem. Okay, let me clean this. So a long straight wire and a small rectangular wire loop lie in the same plane, like this. And you'd like to determine the mutual inductance in terms of L1, L2, okay, L1, L2, and W. And we assume that the wire, this wire, is very long compared to L1, L2, and W, and that the rest of its circuits is very far away compared to L1, L2. So basically think of this as like an infinite wire. So B, yes, thank you. It's mu0 divided by 2 pi, the current divided by distance. So if you are at a distance, let's call this R, that's the magnetic field. And by right-hand rule, this is going to be into the page. And we can see this magnetic field depends on the distance. So we have to find a region in which magnetic field is constant so that we can calculate the flux. For that, I'm going to choose a strip like this. Something like that. And this one is the R. And the flux, magnetic flux, or this magnetic flux in this little region, let's call it d phi b, is equal to, okay, it's B times area. It's going to be equal to mu0 over 2 pi I over R, and area is W times dr. If we integrate, we get the total flux. It's going to be equal to mu0 over 2 pi I times W. It's like a logarithm, and the limits are going from L1 to L2. I'll just write the result because we had this kind of integral a lot in this course. And now d phi b dt is equal to, the only thing that depends on time is the current. So I'm going to write everything like constant in front, W, ln, L2, L1, di, dt. And we know this is going to be equal to induced EMF. And the definition of mutual inductance is the coefficient of this di dt when you find the induced EMF. And that coefficient is here. So m is going to be equal to mu0 over 2 pi w ln L2 over L1. The mutual inductance is defined by something like this, m times di dt. So when you find the induced EMF, and when you write it in terms of di dt, the coefficient in front is going to be mutual inductance. So maybe I can put it like definition. Actually, kind of looks like absolute value. I don't like that. All right, next. Okay, clean this up. So this is like a similar problem. A toroid has a rectangular cross section as shown in figure. Like this cross section is nicely rectangular. Show that the self-inductance is given by this expression, where n is total number of turns, R1 and R2 and H are the dimensions. Like, okay, this is R1, this one is R2, and H is the height as shown in the figure. And we'd like to use Ampere's law to get B as a function of, okay, B. How do I get, okay, actually it says already use Ampere's law. So I'll write Ampere's law. Does anybody remember Ampere's law? It's going to be B dot dl is equal to some mu0 times I enclosed. And for my Amperian loop, let's choose an Amperian loop. I want to choose a line that goes through this donut, like this. And for its radius, I want to choose something like R, okay? So this line penetrates through the squares, each square in this plane, okay? And if I do this, I need to count the number of enclosed currents. The number of enclosed currents, you can see, okay, they don't give you the direction of the current, but we can tell, right? It's like, if there is like currents like this, you enclose each of these currents in your Amperian loop. However many, all of them are inside this Amperian loop. And all the others going in outside, they are not enclosed, they're outside. Okay, they are like this. So these are not included. Good. So I need to count total number of these lines and put it in my enclosed current. And it's easy. Then it is basically let's choose a proper color. This is going to be mu0 times the current of each wire times number of loops. And on this side, for a given circle like this, B is constant. So I'm going to write it like B times, and the circumference is 2 pi r. Then my B is going to be equal to mu0 over 2 pi n times I over r. So now I calculate the flux. Flux is like this B. Okay, now B at this point is different from B at this point and B at this point. So let's just draw a cross section, something like that. So this is the rectangular cross section, and for a given R, you have this B, and we need to calculate this little strip. This is dr, and the height is what? H. And my flux, let me write it here, is going to be equal to, again, this is like infinitesimal flux contribution to this. When I sum over all of them, I'll get the total flux. So this is going to be equal to mu0 over 2 pi n I over R. This is B times area. Area is dr times H. And again, I have 1 over R type of integral, and the limits of integral are going from R1 to R2. So this phi is going to be equal to mu0. Okay, also I forgot. So this is for 1 square, but my total flux should include all of these squares, and there are n of them. So I'll have to multiply this whole thing with one more factor of n. So this is mu0 over 2 pi n squared times h. And again, this is 1 over r integral, which is ln r2 over r1. And we do the same thing, d phi dt. Take the derivative. This is mu0 over 2 pi. Okay, there is an overall I forgot here. Okay. N square h ln r2 r1 times di dt. This is the definition of induced EMF, and the coefficient of di dt is my mutual inductance. So let me just take this here, just open up some space. Then again, m is going to be equal to mu0 over 2 pi n square h ln r2 over r1, which is actually already given here. All right, next. Okay, clean. So calculate the magnetic and electric energy. Okay, actually I want to keep that figure. Let's clear everything else. Calculate the magnetic and electric energy densities at the surface of a 3 millimeter diameter copper wire carrying a 15 ampere current. So you have a copper wire, its diameter is 3 millimeters, so radius is 1.5 millimeters. And you pass a current I, 15 ampere, and you'd like to calculate magnetic and electric energy densities at the surface, anywhere in the surface. So I remind you, magnetic energy density is 1 over 2 mu0 b squared, and electric field energy density is 1 over 2 epsilon 0. Oops, this is E squared. I need to find E and B. So for B, I choose again an Amperian loop right on the surface. And for this, I can just do again Ampere's law. B dot dl is equal to mu0 times I enclosed. In this case, enclosed current is all the current you have, which is I. Then, okay, this is again here, B times 2 pi r. Then B is equal to mu0 over 2 pi I over r. Then magnetic energy density is going to be equal to 1 over 2 mu0 b squared, which is mu0 squared over 4 pi squared and I squared over R squared, but this thing is equal to, open up some space. This thing is equal to, cancel these, mu 0 over 8 pi squared I0 I squared over R squared. Okay. How about the electric field? How about this term? Any ideas? What can I do for this? How can I calculate the electric field? Is there an electric field? Is there really a non-zero electric field in this problem? Yes. So there is current. For the current to exist, somebody must be pushing it. There must be a force on the charges, otherwise there will be no, yes, exactly, there will be no current, then there must be an electric field. And for that, I would like to remind you, okay, maybe we can start from this J. Does anybody remember the relationship between current density J and the electric field? How are they related? J versus E. What is the relation J and E? Exactly, thank you. So I prefer to write it like this, some sigma, and this is given to be a copper wire, so this is copper, if you like, times E. Okay, I can delete this. So I multiply both sides with A, and this side, so A is this cross section, A is equal to pi R squared. This side is I, then I can solve it for electric field. Electric field is going to be equal to I divided by sigma copper times area. And its direction is obviously this, up. Whereas the direction of magnetic field, if you use your right-hand rule, it's going to be at this location into the page, but you know it's going to be circular. So at any point, you have like circles of magnetic field, like this, and you have these lines of electric field. Every single wire has this, right? Which is interesting. That's part of nature. You have these fields in your cable. Yeah, anyways, so let's move on. So the density is, energy density of electric field is going to be 1 over 2 epsilon 0. And I take the square of E, this is I squared over sigma copper square times area squared. Okay, so one is this one, the other one is this one. And I think you can put the numbers. Here, current is given, radius is given. You can calculate area, and you can look at the conductivity of copper from your book. This is conductivity of copper. And that's it. So this is the last suggested problem. In the circuit of figure here, determine the current in each resistor, I1, I2, and I3. At the moment A, the switch is closed. As soon as you close the switch, determine the currents. And B, a long time after the switch is closed. So A, when the switch is closed. So what does the inductor do? As soon as you close the switch, what do you expect the inductor to do? Suppose this is the circuit, I close the switch, and I look at the inductor. What am I going to see? Yes, it is going to counter the currents, but at t is equal to 0, is it going to do anything? Of course, it's going to counter the currents, but immediately after you close the switch. So here is what we saw, right? Let me show you that plot. So as soon as you close the switch here, it's almost as if like nothing passes through inductor. So here is it similar. So as soon as you close inductor, the current inductor is going to be like a brick wall at t is equal to 0. There will be no current. So it's going to be equal to I3 is going to be equal to 0. There will be no current. Then everything should be happening at I2, I1, and I2. We know how to calculate that. So I1 is going to be equal to, I2 is going to be equal to this battery divided by R1 plus R2. Now, long time after the switch is closed, B. After long time, let's call t is equal to infinity. What is going to happen at t is equal to infinity? Let's go back to our picture again. Here, at t is equal to infinity, it's almost as if there is nothing, right? It's almost as if there's no inductor. Inductor did what it can do, and then this circuit reached its steady state. So there is nothing you can do here. You can completely neglect inductor. So that's what I will do here. It's like no L. Then I need to calculate the REQ. So REQ is going to be equal to R1 plus 1 over R2 plus 1 over R3 to the minus 1, which is going to be equal to R1 plus R2, R3 divided by R2 plus R3. And this is equal to, okay, let's just write it like R1, R2 plus R1, R3 plus R2, R3 divided by R2 plus 3, then I1 is going to be equal to E over this REQ, which is going to be times R2 plus R3, divide this whole thing with 1, R2, R1, R3, R2, R3. And the currents between I2 and, okay, what do I know? I know the Kirchhoff's law. I1 should be equal to I2 plus I3, and I also know R2 should be equal to R3, R3, then let's solve it for R3 is equal to R2 over R3 times I2. Then this thing, okay, let's write it like that. I1, okay, I will write it here. So if I1 is equal to I2 plus I3, and this is equal to I2 inside 1 plus R2 over R3, and I2 is going to be equal to R3 divided by R1 plus R2 plus R3 times I1, and this is going to be equal to E R3 divided by, okay, I don't want to write this whole thing again. Copy, paste. And similarly, if you do it for I3, I can kind of see the pattern. So it's going to be equal to copy, something like that. I copied exactly the same thing, but this one should be 2. And finally, what does it say? Maybe I can write all of these guys to here to open up some space. Let's see if I need more space. After the switch has been closed for a long time and then reopened, what is each current just after it is open and D after a long time? Okay, so just after it is open, I can kind of see I1 is going to be equal to 0, right? And now the current is going to be flowing through here, and L is going to behave as if it is like a battery. So for that, I2 should be equal to minus I3, right? And I2 is going to be whatever it was at the moment you close the switch. So it is going to be equal to, okay, whatever it was here, I just copy. Paste. And again, the other one is with the minus sign. This one. Okay. And I think that's it. D after a long time. So D after a long time, basically everything that can happen will happen and it will dissipate. So basically there will be nothing. I1 is equal to I2 is equal to I3 is equal to 0. All energy dissipated at the resistors, and you run out of gas. Any comments? All right, then congratulations. That's the end of this class.